This is a summary on value function approximation. So in this lecture, we actually found out that in practice it is often needed to approximate the value function because of a variety of reasons. The first one, or the most integral one, is that explicit tabular representations simply require too much space, and we usually do not have so much space in our state-of-the-art memory in our computers. And another idea also was that while using explicit representations, we are not really generalizing the information across nearby states. This is also related to the idea of partially observable Markov decision processes. We then saw that linear function approximation is actually deriving a set of features from our state space and linearly combining them using parameters that we estimate is possible in practice, and almost all our convergence properties hold. However, actually it is not really easy to come up with a representative set of features that we can use for linear function approximation. However, nonlinear function approximation instead does not guarantee any of such guarantees that we currently assume in reinforcement learning, and this is also why careful scheduling and several tricks are needed to actually stabilize training in practice. So actually see if you want actually to read a little bit more about it, there is like a nice video that's really like worth watching in here. And also here, I think this is a blog post, which is maybe you should really like read it with humor. This is actually showing you situations why reinforcement learning and value function approximation doesn't work in practice, and you can read along. It's really funny to read this. Now, with value function approximation, we have seen a lot of problems that we're actually facing with reinforcement learning, and there is one kind of idea behind that we usually use when we talk about reinforcement learning, and it is called the Deadly Triad. So the Deadly Triad, you will also find it in the Sutton and Bartos reinforcement learning book. But the Deadly Triad defines the problem of stability in reinforcement learning and in the training process. And stability in reinforcement learning is really a serious thing. This is actually the most serious thing we're any time talking about or actually complain with. And it usually stems from three different problematic issues. The first one is that we approximate the value function, and under approximate representations we add the noise that we have in our approximation. They usually lead to a bias when we actually calculate our targets, and then this might be very problematic in practice. And this also is very much related to our bootstrapping issue, because we're actually having no ground truth that we're actually optimizing to. We train a network, and we use this network to actually generate the targets we are actually optimizing towards by itself. And if we actually train something that we also use to calculate our estimation targets or learning targets, of course this is problematic in practice. And also the general thing of off-policy training is also already something very very problematic, as with the off-policy training we're actually not any longer we're not really sticking to the generalized policy iteration scheme that we defined in the beginning. So with off-policy we already violate the problematic issues we had in the beginning. And unfortunately, in most of our cases where we actually do reinforcement learning in practice, we have the full combination of all these things, and this is why the Deadly Triad is really a problem in practice. The Deadly Triad is also something that is like really something related to reinforcement learning. So if you Google Deadly Triad, I don't know, I think it's already a little bit older, but you really like Google gives you really results really connected to reinforcement learning. One thing also to mention, I didn't know where I really should put it in. There is a really nice work that's really like very recent, is on this year's ICLR. It's from Pan and Martha White from Canada, and it's called fuzzy tiling activations. So the idea basically in DQNs and in the stationary, so actually the problem that we bootstrapping our Q targets, and we have this problem of a network that predicts its target and also optimizes in the same area. We can actually what we actually did is we actually introduced a second network, a target network, to have more stable targets. But it's still not really intuitive how to optimally choose the K factor in order to not delay training that much, because we stabilize training, but we're always using information that's too old already. What we usually want to have is we want to optimize our values towards the most recent information that we got from the environment. And this is very much delayed for depending on how you actually use and how you actually choose K in this case. And what you actually, and there's an idea of the lab in Alberta in here, where you actually try to build sparse representations in your value network, in your neural network. So actually what you had with the tile coding idea that we saw from linear value function approximation, what you got is a one-hot encoding of activations or of certain tiles. And if you optimize such a one-hot encoding, you really do not optimize anything related to nearby Q values, because they have a different encoding. So you would actually, through such a one-hot encoding, you will actually have not if you're just optimizing towards one of these Q values, you will not that much affect the Q through your gradient descent step. You would not that much affect the value or this effect has on nearby Q values. So this is actually why we introduced target networks, because a gradient descent step of the Q values affects the nearby Q values as well. And this is something we can get away with if we introduce sparse representations in the feature space. And this is actually what fuzzy tiling activation tries to actually achieve. They actually introduce an FTA layer, so a fuzzy tiling activation layer, which actually takes the output of a hidden layer and transforms it into a sparse representation that is in the ideal case either 0 or 1, but with a small transaction in between where the gradients are not really 0, and it's differentiable in this case. And what you then actually can assure is that an update on a certain Q value on here within a single network does not affect nearby Q values, so actually does not affect your targets that you actually use to calculate your loss function. And this is a very nice idea that actually combines the idea of tile coding from linear functional approximation into the strong nonlinear activations in neural networks, and then you can combine both of them, and you in the end can get away without using target networks after all. What do I want to actually, what is actually the lesson of today? So what's the lesson of this video? What I want to show you, nonlinear functional approximation could be really problematic in practice. You have the problem of divergence because you actually bootstrap your values, and if you keep on updating through your through network while also predicting the targets, this can lead to divergence, and this is a serious issue in reinforcement learning. If you want further reading, this is literature I can recommend to you, and if not, we will in the next videos talk about policy-based reinforcement learning.